Do you know that problem? Your images are noisy because the illumination was just too weak. Today we are going to create a super simple device to measure the illumination intensity. I also explain how to use the characteristic curves of a solar cell to engineer the right circuitry. Professional video makers are measuring the illumination before they even turn on their cameras, and with good reason. I'm not a professional, but I still thought by myself, it would be good if I could measure if the lighting is bright enough for a video in advance. That would save me a lot of effort for repeating the recording, because I often only noticed when editing that some pictures and videos were noisy. Simple commercial illuminance measuring devices are setting you back by about 30 euros. Professional equipment is rather at 1000 euros. But in my case, a rather simple solution is really sufficient. Recently, I reached into my junk box, and that was when I had the idea to create a light intensity meter out of an old moving coil instrument and a solar cell. It turned out to be the simplest electronics project I've ever built. But I like it very much, especially because the device does not need batteries. I made a few more thoughts on the circuitry that I would like to share with you briefly, because it's actually very interesting. Illuminance, which is incidentally measured in lux, can vary over a very wide range. For example, on a sunny day we measure 130,000 lux outside, we measure about 500 lux in an office, and a candle in a distance of 1 meter is producing 1 lux. And this is practically the measuring range I need for my purpose. It comprises 5 orders of magnitude. Of course, such a large range cannot be displayed on an analog measuring instrument. That's why I use a potentiometer in order to extend the measuring range. And then I connected 2 Schottky diodes in parallel with the meter. And the diodes are for overvoltage protection of the sensitive moving coil measuring instrument, which deflects fully at 100 microamps. Since the instrument has a coil resistance of 2 kilo ohms, full-scale deflection is reached at 0.2 volts. With the 2 Schottky diodes, we limit the voltage to about 1.5 volts. The wiring of the potentiometer looks somehow strange, at least it's not what you would expect at a first glance. Why did I do it like this? To explain this, let's look at the characteristic curve of a solar cell. Actually, you will hardly find any information about how a solar cell behaves at low light conditions. I have therefore extrapolated the characteristic curves down to very low illumination levels. From sunlight to an illumination level that is 5 orders of magnitude lower. And the latter corresponds approximately to the brightness of a candle. With a linear scale on the y-axis, we can of course not display the associated characteristic curves, as you can see here. That's why I am using a logarithmic scale now. As a result, we can see the very low currents that the solar cell delivers at low light. If we would now simply take the voltage as a measure for the radiation intensity, then we had the following problem. The voltage changes only slightly with higher illumination intensity. And therefore, it would be not very wise to derive a measurement method from it. We actually want to measure the current, which is proportional to the illuminance. So we let the current flow through a resistor. And then we use the voltage drop to measure the current, so to speak. If I draw a resistance on the diagram, it looks something like this. In the linear representation, a resistance is simply represented by a straight line. In this case, it would be a relatively small resistance. We can already see that this would be a good method for measuring a high level of illumination, because the voltage across the resistor varies very nicely with the level of illumination. If we want to measure small illuminances, then we increase the resistance. In order to understand this, we now have to go back to the logarithmic representation. By the way, a resistance is no longer a straight line in that diagram. We can see very nicely in this chart that we can cover the entire range by increasing the measuring resistor. We always get an almost proportional voltage in relation to the illuminance. This is exactly what we achieve with this strange wiring of the potentiometer. After I saw that this principle works very well, I designed a housing for it and had it printed by my nephew. I think he is enjoying my projects more and more. The housing consists of a body and a front panel, which has the appropriate holes for the solar cell, the moving coil instrument and the potentiometer. Incidentally, the whole thing also inspired me to construct a standard housing that can be defined via parameters. This way, you can design a new case in a flash by just entering a few dimensions. But more on that later. The assembly was super quick. With the self-made device, I can now measure the illuminance before I record a video. Actually, I don't measure the exact illuminance, I rather make comparisons. I have to say that the simple device works very well and, as I said, completely battery-free. That's really a sustainable project, isn't it? And by using scrap parts, I had practically zero cost apart from the filament for the 3D printer. I would like to give you a few reference values for the case you want to build the project yourself. If the potentiometer is turned all the way to the right, you can measure in the range of about 1 to 1000 lux. When the potentiometer is in the 50% position, you get full deflection on a cloudy sky, which corresponds up to about 10,000 lux. If you turn the potentiometer further to the left, you can measure in sunlight and even above. By the way, 1 watt of radiant power per square meter corresponds to about 683 lux. The files for the 3D printer are available in the download area below. Happy making! Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.